great.
The next speaker is going to be Tengyu, and he's going to give us a view of the optimization landscape of matrix and tensor decomposition process.
Okay, great. Thanks for coming. Thanks for having me here. So I'm Tengyu. This is based on joint work with Jason Lee from USC and Rongo from Duke University. I'm at Facebook AI Research as a visiting scientist for this year, and I'll be joining Stanford afterwards. So I'd like to start by discussing a little bit about what I see as the interfaces between users and optimizers for the machine learning settings. So let's first discuss what's the typical interfaces between users and optimization researchers. Right, it's kind of simple, right? So the users send a function to the optimizers, so it describes the function, and the optimizers needs to decide what to do. The optimization researchers decide what to do. Maybe we use a very simple algorithm like gradient descent or local search algorithm for discrete case. Or we could, if the problem is very complicated, maybe we need to use some convectorization or rounding, or maybe we need some other algorithms. But it doesn't matter what algorithms we use. Then at the end of the day, we need to send the solution back to the user, and that's it. So and the solution needs to satisfy the original constraints, and so on and so forth. Right? If the original problem is discrete optimization, then we need to send back discrete solutions. So and in machine learning, in the past several years, people have been make this interface a little bit more flexible, and by having more kind of features. This is not in the past few years, but for a lot of years, people have studied various different settings. For example, you can describe a set of different features about the functions. For example, f is a function, is a sum of functions, and each of these fi's could be convex, smooth, strongly convex, so on and so forth, and could be have some condition number, condition, so on and so forth. So you have a list of small set of features, and then the optimization researcher needs to decide what algorithm to use. When you have a sum of functions, maybe stochastic descent is a good algorithm, or maybe you can use some advanced version like Saga, SDCA, SVRG, so on and so forth. And of course, at the end of the day, you still need to find a solution and send it back to the user. So what I would like to argue here is that maybe in machine learning nowadays, in modern machine learning, we can have some slightly different, more flexible interfaces so that we can, have more progress, especially in a non-convex world. By the way, most of this talk is concerned about, we're concerned about, non-convex optimization. So in a non-convex world, the problem is pretty hard. So maybe we need to be more flexible. So after receiving this function from the users, maybe the first question we need to ask is whether this function is easy for us. You can have different type of interpretation for this question. Maybe this can be interpreted as whether this function is in principle, fundamentally whether we can solve it in polynomial time. Or you can interpret this question as whether we can have a fast algorithm for it. Or you can interpret as whether the existing algorithms can solve it, like stochastic descent can solve it. And if the answer is no, then we need to go back and ask, okay, maybe this function is too hard for us. Can you change the object function? Usually you cannot do this in a classical setting because the function f is really our problem. But in machine learning, we have this flexibility because the users can say, okay, maybe let me try a new model and a new loss function. So just in case you are not very familiar with machine learning, so in machine learning, just recall that, for example, in supervised learning, a model is a parametric function of the input. The input is x, and we have g theta, which is parameterized by theta. And y hat is our prediction. And y is the true label, let's say. And given the true label and the prediction, we can have a loss function, L. And we care often about the expectation of the loss over the distribution of x. So we see that g theta and L are something that we can change possibly, especially the model itself. So we don't really care about the model itself. As long as it has good error, then probably it's fine. So that's why we can change the model and change the loss function. And when we have a new function f prime, and we send it back to the optimization researcher, and probably this function is easy, and we say, okay, let's use some simple algorithm like stochastic gradient descent. And then we send solution for f prime back to the user. And here the important thing is that we don't have to do any rounding because we really just care about f prime. We can already forget about f. We don't have to be good on f. We only need to be good on f prime. So this is a little bit related to what Intek talk about, right? So in Intek's talk, so he has a sequence of smoothing of the original function, but at the end of the day, he still needs to find the solution for the original function. But here we don't really care that much about it. So it's a little bit easier. So, and actually a lot of recent progress, especially empirical progress in deep learning, are really following this paradigm. So ReLU, rectifier linear unit. So this is activation function that replaces the sigmoid in recent days. So this is really just changing the optimization problem and make it easier. And also over-parametrization, meaning you make the model bigger and bigger. And batch optimization and the residual networks are ways to change the model so that optimization becomes easier, so that you can optimize deep models, so on and so forth. So in this talk, I'm not going to really have enough things to support these things. So but what I'm only going to focus on is this question: is this function easy to me? Can we have any mathematical ways to decide what functions are easy? Understanding the landscape of the functions. So so this is the part. Given this thought, this is the kind of paradigm that is possible for optimization theory in machine learning. So the first step, is to identify a family of functions that are tractable. Again, I'm talking about continuous functions, and then we might think, okay, can we decide whether a function belongs to this family F? And the third step is whether we can, design new models and object functions that can provably be in the set F. So I'm not saying that these three steps have to be done in order. We can, and actually, I think that we should, pursue each of these steps, in parallel in some sense. But this might be a reasonable paradigm. And so just to briefly summarize the kind of state of art, the best we know for approximately the best we know for all of these, questions. So for the family of functions, this is probably the largest or one of the largest families of functions that we know how to optimize in continuous world. So if the function satisfies that all local minima, or most of the local minima are approximate global, then we can hope to find the approximate global minima. So for example, basically this is saying that many object functions in machine learning, we conjecture that they have this property, all local minima are global. This is saying that okay, the functions like this doesn't happen that often in machine learning setting. And what really happen often in these kind of functions where you don't have any bad local minima. Right? There are two local minima, they're both global. And the reason why this type of functions is easier is that many local search algorithm converge to a local minimum with arbitrary normalization under additional, if you assume additionally that every saddle point has a strictly negative curvature. So this is not exactly true, but approximately true. So local minimum should be easier to find. And this is also not just a vacuous property. Many object functions in machine learning has been shown to have this property. I don't expect to read this list, but many statistical machine learning questions have shown to have this property. Right. So the next step, is kind of the focus of this talk, right? So how do we decide whether a function belongs to a family F? And this talk I'm going to, kind of survey some of the existing techniques and also, talk about some of the new techniques we're trying from random field and geometry. So I'm not going to talk about anything about the third step, but there are some recent progress in simplified settings, like Morris and Ben and myself. So we have some paper on understanding over-parametrizations for some simple linear dynamical system setting, and there are other papers for over-parametrizations for deep neural networks. And recently with Jason and Ronge, so we have some paper that designs new object functions for like deep learning, one layer, hidden neural networks, one hidden layer networks that we are going to put on archive recently. So, but this is not what I'm going to talk about today. And let me also just to mention that optimization is not only a thing for machine learning. If you care about machine learning, so we also need to care about generalization. But in this talk, I'm not going to talk anything about that. All right. So, so techniques for analyzing the optimization landscape. How can we prove that all local minima are global? So I think there are probably two types of techniques. So most of the techniques that we are using in these papers that I've cited in one of the previous slides is I describe them as explicit analytic uses of optimality conditions. And these techniques are very good for matrix factorization problems. So let me just start with a warm-up. So for eigenvector problems. So let's say suppose we want to compute the top eigenvector. And this is the object functions we want to use. So we maximize just the quadratic form and over the unit sphere. This is just a standard formulation. And the claim is that this object functions has no bad local minima. All local minima is actually the only local minimum. Actually, the only two local minima are the global minimum. So they are just plus minus the top eigenvector. So this will be plus minus v1. There is a symmetry here. So and of course, this is a local maximum on the manifold. So let me have a simple proof sketch for this, just to demonstrate what I mean by explicit analytical use of the optimality conditions. So let's say Px is the projection to the tangent space of the unit sphere, and the gradient on the manifold of the function f is the projection times m times x. And the Hessian, has this formula. We can compute it using some formula from manifold, differential geometry. So it's pretty simple. So the optimality conditions consist of two things, right? So the gradient is 0, and the Hessian is less than 0, right? So that's a necessary conditions for x to be a local maxima, although they are not sufficient. So let's see first what we can have from the gradient is 0. So the gradient 0 means that if you plug in x into this and plug in px is equal to I minus xs transpose and the rearrange, we get m times x is equals to the scalar x transpose mx. This is a scalar times x. So this means that x is an eigenvector. So all the stationary points or critical points are eigenvectors. And now let's look at which eigenvector here can be a local maxima. So now let's look at the Hessian, right? Hessian is less than 0. Because it's less than 0 in the PSD sense, then if plug in any vector, it is still less than 0. So we plug in v1 in the quadratic form. This is less than 0. And this will imply x is equal to v1. And the reason is below. So let's say x is equals to vk, and vk is the k's top eigenvector, which is not, but it's not the top eigenvector, the k's eigenvector, and k is not equal to 1. And we can, with a little calculation, you can compute the quadratic form of the Hessian at vk over v1. So this is equals to basically the eigenvalue, the top eigenvalue minus the k's eigenvalue. And by definition, this is larger than 0. So this basically says that at the point vk, the gradient is 0, but you can move in the direction of v1 to get a second order improvement. That's why it's not a local maximum. So this is how we do the eigenvector problem. And actually similar techniques can be used for analyzing a bunch of problems that relate to matrix factorization. So here are the extensions. So for example, we can do an alternative formulation of top eigenvector. We minimize m minus xs transpose for binom square. And the minimizer of this is the scaling of the top eigenvector. And we can also do SVD PCA with a little bit higher rank, let's say m minus xy transpose for binom square, where x is top, x and y are top matrices. So we can also do matrix completion, which is essentially something like this. So you have m minus xs transpose, and you do a Hartman dot product, entry-wise dot product with kind of a mass matrix, which is like the observation matrix. Omega is a random sparse 0, 1 matrix. And you can also do matrix sensing, where you have this matrix and you apply a linear transformation, and you get a random linear projection, and you measure the L2 norm. So, and all of this, functions have been shown to have the property that all local optima are global. Of course, under certain statistical assumptions for the bullet 3 and 4 case. And sometimes, to deal with some weird corner case, you have to add some regularization terms to make the landscape a little better to have this property. Right. So, and the common proof strategy, as I kind of indicated, are mostly like this. So you have that the gradient is 0, implies some statement about A. Before we have the gradient of 0, it implies X is an eigenvector. And then you have the Hessian is a positive semi-definite. This implies some other statement about the point X. And you combine these two statements, and you get X is a global minimum. And this is basically what I mean by explicit analytical use of the optimality conditions. And for this type of matrix factorization problems, the next thing is that these two matrices, these two statements A and B, or maybe it's not just a single statement, it's a sequence of statements. So all of these statements are often guided by the linear algebraic structures of the problems, because these are all about linear algebra.
So the problems you had in the previous slide, they're all can be formulated as simple SDPs. So just for that, they are, because they're convex optimization.
Yes. So all of these problems can be solved by convex relaxation.
Relaxation, exact for, like the largest eigenvalue can be formulated as a one variable SDP for that.
Yes, so I definitely agree with that. Although I think that might be it might be a little bit trickier than that because you can solve the top eigenvector problem by SDP, but if you look at the SDP solver, you need to compute the hyperrating separate-plane.
The proof that it is unique and all that stuff that follows from the convexity, I think.
The proof of the uniqueness of the local optimal. That I don't. I'm not aware. I think there's certainly quite a deep connections between to the convex case, but I'm just saying that I don't know of any explicit connections.
Like Zi minus A is positive semi-definite minimize Z. That's just a single variable. That's an SDP. That's the solution is.
Yes.
The solution is the eigenvalue to the largest.
Yes, I definitely agree with that. Yes. But I'm just saying that to solve that SDP, you also need to solve eigenvector problems.
But to prove that it is unique, that's for its context.
To prove what is unique?
The previous slide that you had that you were trying to prove that it is. So
no, I'm proving the local maximum of this is not unique. There are two local maxima. I don't think that follows from SDP relaxation. I don't know. I would love to know it if there exists such a proof. Okay. But nevertheless, I'm not saying that this this gives us any strictly powerful algorithms, but they are also in practice they are much faster, and but of course this can be solved by SDPs, right? So okay, so talking about speaking about the proof strategies. And also, this type of proof strategies are often very good for those situations where we have some rotational invariance in the problems, which also probably related to some of the SDP stuffs. So, and for example, if you look at this PCA objective, if you have some rotation R and then you right rotate X and Y, you get X times R and Y times R, and you get exactly the same equivalent, solutions in terms of the function value. So, and it seems that this type of techniques might be a little bit limited, especially because we need to kind of solve, in some sense, this statement A is a way to kind of solve, the first order critical point solution, the first order critical point optimality conditions. So, so basically, it seems that this type of techniques is a little bit restricted to the problems with rotational invariance, and we are looking for whether there's any other techniques for analyzing landscapes. So that's what I'm going to talk about in the next 20 minutes. So the techniques that we are trying to use is Kac-Rice formula. This is a counting technique that tries to count how many local minima of a function. So let me just to define the problem that we are using this Kac-Rice formula on. So the problem definition for tensor decomposition is that we are given a tensor T of the form that T is a sum of rank 1 tensor. So this is a sum of AI to the tensor power 4. Each of these AIs is a d-dimensional vector. So T is a d times d times d times d dimensional tensor. And we are given the entries of T, and our goal is to find the component AI. So of course we need to make some assumptions on AI so that we can recover all of the AIs. Let me specify that in a moment. So the feature of this problem is that it is a little bit beyond linear algebra. So T only has some permutation invariance. You can only permute AIs. You can permute AIs in any way, and you get the same T, but you cannot rotate them to get the same T. So, so this is a little bit beyond the cases that we know how to solve. And a non-convex program that we are interested in is the following. We just maximize the injective norm of T. So basically, we have a variable x, and we maximize the inner product between T and x to the tensor power 4. And because T is of this structure, so actually these object functions can be written as a sum of ai dot x to the power 4. And we maximize it over the unit sphere. Empirically, if these AIs are random, then for a large range of parameters n and d, gradient descent finds one of the AIs empirically when AIs are random.
Yes, what's a rank for which it happens?
So empirically we can only test it for I think I tested for dimension d like 1,000. So we believe that theoretically we hope that this is true for n is less than d squared.
Compared to the dimension d squared?
Yeah, d squared. But empirically we cannot test that thoroughly, because if d is 1,000, then n is 1,000 squared, then we don't have the computational power to really test it that thoroughly. So yeah, I'm just talking about the empirical fact. Yeah. So empirically I don't know exactly, but I believe it could be d squared. I don't know. So and the question is, can we explain this by characterizing the landscape of function f? Let me also just mention that, again, this is a problem that can be solved by semi-definite programming. So certain cases can be solved in polynomial time. So there's a full B algorithm, and also we have developed a sum of squares algorithm for it, and there are speed up of sum of squares algorithm for some certain cases. But here,
if the AIs are random but sparse, do those techniques work equally well, or?
I think for the sum of squares algorithm that we did with Jonathan David, I would guess there is a good hope. Because the techniques there is pretty generic, and you only need to establish some inequalities for some inequalities via sum of squares proofs. So I think there's a good chance that it can still work.
But this non-convex programming approach, do you think will also work in a sparse case?
Non-convex programming approach? I don't know. I think there's a chance that it can still work. Yeah. Yeah. All right. So yeah. So but the point here, yes. Again, the point here is that we are trying to understand the non-convex maximization. So just to give some intuition, so the easy case is the case when all of the AIs are orthogonal. And when they are orthogonal, actually we can, without loss of derivative, assume that each of the AIs is just the natural basis vector. And then the object functions just becomes that each of the AIs is EI. Then this is just the sum of the fourth, the fourth power of each of the coordinates. It's just the fourth norm to the power 4. And the constraint is that the 2 norm is 1. So, and the global maxima is exactly x equals to EI for I from 1 to d. And the value has of the function is 1. And we can prove that all local minima are global, and actually the proof is also pretty straightforward. It follows from this kind of explicit analytical uses of homogeneity conditions. So if x is a stationary point, you can write down the gradient. And basically the way to think about it is that if the gradient 0 means that you cannot move on a manifold to any place. So basically means that the ambient gradient is parallel to x. And if you solve that equation, you can get that x really have to be of this kind of form, right? So all of the entries each of the coordinates can only take 3 entries, plus c, minus c, and 0. And then you look at all of these possible critical points. There are kind of exponential number of such critical points. And you look at, compute the Hessian for all of them, and you will see that only x is equal to EI can be local maxima, and all of the others are not saddle points. So this is kind of the easy case, and the hard case is the over-complete case when n is larger than d. So the rank is larger than dimension, and we make the assumption, the randomness assumption, just to make the problem a little bit easier. So we assume that each of the AIs are random from random Gaussian. So we choose the covariance to be 1 over d times identity just to make sure that AI is roughly unit norm. So, and we have the same object function, and we know that the global maxima are approximately, plus minus a1 up to plus minus an. So, and this can be proved easily, with a little calculation using some, concentration inequality. We can show that for all x, f of x is less than 1 plus epsilon. Epsilon depends on the parameters like n and d, and you can also show that for every AI, it also achieves a value around 1. And you can also show that if the function value is close to 1, then x has to be close to one of the plus minus AIs. So this all of this can be done by concentration inequalities. And we care about the local maxima, and this is what we can prove. It's not a complete result, as you can see. So we can prove that fx has exactly 2n local optima, 2n local maxima, and they are roughly equals to plus minus a1 up to plus minus an in the superlevel set that contains all of the x such that the function value is larger than 1.01 times the value for random initialization. So the value for random initialization basically is expectation of fx, by taking expectation over the random choice of x. And this is actually equals to 3n over d squared. And in our parameter setting, this is much less than 1. So basically, the kind of idea is that we have the landscape look like this. This is a plot for actually a 3-dimensional case. So there are all of these local maxima, a1, a2, a3, and minus a1, minus a2, minus a3. And so the largest values are 1, and the expected value is 3n over d squared. And what we can do is that we can show that in this region there is no bad local minima, optima, bad local maxima. And but between here we don't really know what happens. And let me just mention that actually between here there are a lot of points here. Like actually the probability measure in this region is close to 1. So we cannot randomly initialize to get into this region. Although from another point of view, this region should be pretty easy for optimization. If you run the experiment, with a few number of steps, you get into this superlevel set. And actually we conjecture that with constant number of steps, you can get into the superlevel set, but don't know how to prove it. Right. So this is what we can prove. And now let me talk about the techniques. So we're using this Kac-Rice formula. So this Kac-Rice formula is a general techniques to count how many local minima for that a function has. Actually, it can be even more general than that, as you can see. So the general setting is that we have two random functions. Actually, these are two random two random vector field. So P is a function from d dimension to d dimension, and Q is a function from d dimension to k dimension. And we have a set B, which is in k dimension. And we care about this integer random variable. This number n is equals to the number of points such that Px is equal to 0, and Qx is in the set B. And we care about the expectation of this number, of this random variable. And here is the formula. So under certain regulatory conditions, the expectation of n is equals to this, this quantity. So it's the integral over dx, and the integrand is an expectation of, a bunch of quantities. Okay, so the full proofs, can be found in Adler and Taylor, and there's a long history of work on this type of formulas. So the intuition is that it's kind of really just the switching of expectation integral. So the first thing to prove this formula, the first thing you want to do is that you want to write n as an integral. So you write n as an integral over dx, and this is basically an indicator function in some sense, but it's a it's an approximate indicator function, and this determinant of gradient of p is kind of the Jacobian to do the change of variable, and that doesn't really matter that much. So basically, you write n as integral over x, and then you take expectation for n, and then you change the order of expectation and integral properly. So it's basically a counting technique. In some sense, you can think of this as, for every point, I want to count what is the chance that this point is a local minima, and then I add up the chance. But of course, that's a kind of the discrete way of thinking about it. Okay, so, and you can see, because this is very general, you can use this to count how many local maxima. Basically, the only thing we do is, let's say we have a function f, and we take p in the previous slide to be the gradient of f, and q in the previous slide to be the Hessian of f, the magnitude of the Hessian of f. And then you take b to be the set of positive semi-definite matrices, and then the number of local maxima is just equals to the number of points such that px is 0, which means the gradient is 0, and qx is positive semi-definite, which means that the original function, has a negative Hessian. And you just plug in p and q with these two choices, and you get this complete formula. All right. So, and then you can extend this to random functions on the manifold, which is the case that we care about. You only need to replace gradient and gradient square by the gradient and Hessian on the manifold. And you can also extend this to the setting where you only care about a superlevel set. Maybe I should skip this slide because I have limited time. But it's kind of trivial. The only thing you need to do is you need to have an indicator here to indicate the superlevel set. But let's not care about this. I guess I have limited time, but let me still do the simple case for spherical spin glass model. So this is by Alfinger et al., and they want to care about, they want to count how many local minima at different level set of this that this random function has. So this is a completely random polynomial. So our case is a structured random polynomial, but this is a completely random polynomial. And for this case, actually, it's relatively straightforward to use this formula, because you can compute the distribution of the gradient, and it turns out to be a Gaussian vector, and the distribution of the Hessian turns out to be a Gaussian orthogonal ensemble matrix. And this can be verified easily. Maybe let me skip this. So basically, the point here is that if you look at this formula, every quantity in this formula has a known density. If you look at this formula, it only depends on the Hessian through the spectrum of the Hessian, because you only care about the determinant of the Hessian. And all of the quantities actually have closed form. So the eigenvalue distribution of the Hessian has closed form because it's GOE matrix, and so is for everything else. So basically, you use this formula, you can get the expectation of n, and the conclusion that they have from this paper is that most of the local minima have similar function values.
Sorry, what does the last factor mean, the p of the gradient of fx?
Yeah, so this is, this notation is a little bit, probably a little bit not rigorous. So this is the density of the gradient. Sorry, let me see. So this is the density of the gradient evaluated at 0. So without the 0, this is the density of the gradient, and you evaluate it at 0. Because you care about when the gradient is equal to 0. That's why you put 0 here. If you care about when the gradient is equal to u, then you put u here. All right. So, okay, let's go back to our polynomial. Our polynomial is a sum of random linear polynomial to the power of 4. So we can compute the gradient Hessian. So if you do a little bit change of variable, you define alpha I to be the inner product of AI and x, and bi to be the projection of AI to the tangent space. Then we can write the gradient Hessian as follows. So the gradient is a sum of alpha I cubed times bi, and the Hessian has this formula. So the exact formula doesn't really matter. So and alpha I has Gaussian distribution, and bi also has Gaussian distribution. And the good news is that the distribution of the gradient and the Hessian don't really depend on x, because the whole system is a rotational invariant. So you don't really care about x. So the integral over x is not an issue. But the bad news is that the Hessian, we don't have closed form formula for the eigenvalue distribution of the Hessian, because the Hessian looks like this. So this is kind of like a weight-shard matrix, but actually there's a generalized weight-shard matrix with some weighting in front of each of the term, and the weight is also a square of the Gaussian, and you also have some random identity, a random scalar times identity. So that's kind of the bad news, and so basically we don't know the exact eigenvalue distribution for the Hessian. So the question is, how do we evaluate the Kac-Rice formula? So there are two ideas that I'm going to discuss in this talk. So the first idea is that how do we change the evaluation problem to an estimation problem? The Kac-Rice formula gives you exact formula for the exact expectation, and but we don't know how to compute that. Maybe we want to do some inequality instead of equality. So the trick is that we divide the level set into two level sets. Right, the first set is the set of S1 that contains all of the points with function value very close to 1. So in some sense, this is the set of points that are very close to a global minimum. And S2 is the rest of them. So, and of course, the local maximum, number of local maxima in S is equals to the number of local maxima in both of these two sets. And we use different techniques for these two sets. For the first set, where this contains the set of points that they are close to global optima, then we use some other analytical techniques that we kind of similar to what we described in the first part of the talk. So this doesn't use Kac-Rice formula. And for this part, we use Kac-Rice formula, but we use the estimated version of it. We compute the expected number of local maxima in S2, and we found that it's less than an inverse exponential. And that means that with high probability, this number, the number of local maxima in S2, is exactly 0. So this is how you avoid the issue of evaluating the formula exactly. So you only need to have this type of estimation instead of exact evaluation. Right. So so basically you only need the upper bound for the Kac-Rice formula. So now how do we have an upper bound? So recall that we still have the determinant issue, right? So we had this determinant of the Hessian. And for most of part of the paper, we basically use this simple AMGM inequality to bound the determinant. So we have the determinant of a matrix M times the indicator that M is a PSD matrix is less than the average of the eigenvalue to the power D, right? Basically, this is the product of eigenvalues, and condition on the eigenvalues are positive. And it's a product of n things, d things, and you bound it by the average of them to the power d. And this is reasonably tight when M has similar eigenvalues, which is kind of the case for us, because M is a random matrix. And of course, we also need other random matrix bounds for cases when this is not tight. There are multiple different subcases that we need to deal differently using random matrix theory. So So basically, I think let me just briefly discuss, before wrapping up, let me briefly discuss why we can only do it for the superlevel set, but not for the overall sphere. So as I said, the first difficulty is that when the function value fx when fx is very close to expected fx, which means that x is not in the level set, then the Hessian is roughly a generalized weight-shard matrix with mean 0. And when it has mean 0, this type of inequality is not very tight at all, because in most of the cases, this indicator, in some sense, the eigenvalues are not equal anymore. In some sense. And difficult too is that I think this is even more fundamental, which is here we have to care about all the inverse exponential probability event. So the standard random matrix theory doesn't really suffice, because especially the type of high probability event is not the only thing we have to care about. We also need to care about those events with very high probability. This is because at the end of the day we have to take an integral over all point x, and that means that you multiply the whole thing by exponential. So which means that the exponential matters, and actually the base in the exponential matters. All right, so let me just use 1 minute to discuss the open question. So the open question, as I alluded basically is whether we can prove that the projected gradient ascent from random initialization can converge to approximately one of the AIs. And so again, basically the missing part is what happens in this region. And there are two possibilities. One is that there are exactly two local minima, optima, on the whole unit sphere. If that's the case, then we can prove this algorithmic result. But actually, I don't strongly believe in this because we did some heuristical calculation and tried to count how many local minima here. And it turns out, our calculation is not rigorous, and the number we got is very close to 1 to the power d. Like it's kind of like 0.95 to the power d. So you see that it's a little bit tricky because if we did the calculation a little bit wrongly, or some of the approximation is not quite correct, it might be larger than 1. So that's why I wouldn't strongly believe in this, but empirically this conjecture is true, sounds like true. So another possibility is that from random initialization, after one step of projected gradient ascent, the iterates fall into the superlevel set S. So it's possible that there are some bad local optima here, but you just never hit it because you start with random initialization. And we do have a specific reason to conjecture that there is only O of 1 steps. There are only O of steps. You only need big O of 1 steps because if you believe that at the first constant number of steps, you can always make the same type of progress as what you make in the first step, then you're going to have this. Of course, that's not a proof, but that's how we got number of 1. All right, so okay. So just to wrap up, so I've discussed two types of techniques for understanding the landscape of the optimization functions. So one is using explicit analytical uses of optimality conditions, and the other is to use Kac-Rice formula and random matrix theory. And of course, one of the open questions, a broader open question is whether we can have more mathematical techniques to analyze the optimization landscape. Thank you.
Questions?
Madi?
So in the S2 region, is it the case that uniform concentration doesn't happen, so that you have to use Kac-Rice, or
in which region?
in like the S2 region, because there was one region where you didn't use Kac-Rice formula, the other region you used it.
Yes.
Is it that in that region you cannot have uniform concentration results, or?
No, I think the most of the reason is that we don't know how to solve the gradient is 0 equation, right? So in the region we use Kac-Rice, basically we want to we don't know nothing about that region, right? We don't know where the critical points are. We don't know whether we don't have any clue. So it's very hard to use any analytical tools. That's most of the problem. And for the reason actually, are you asking for the reason we don't use Kac-Rice?
No. Why are you using it? I'm saying like the Hessian and the gradient look simple, and I was thinking, is it possible to show that it concentrates around its expected value, and so you infer from that something?
It's I don't think it's concentrated around the expected value. It cannot be, right? Because you are looking at the whole unit sphere, right? So the expected value for every point is always the same. Because this is rotational. So if you look at the expectation of the gradient with respect to the randomness, then it's always the same. So, but of course, if you fix the random vectors, then you look at the gradient at every point, then they cannot be the same. So the concentration doesn't work. Yeah, probably that's the shortest answer. Yeah.
Can you go to that theorem that had 1.01 in it?
Oh, okay. So the main theorem.
You passed it.
Oh, sorry. No, I think I gave it earlier, right?
Here?
Yeah.
I cannot parse this set S. It says x is such that if x is greater than or equal to some number times the sentence.
Oh, so okay. So the easiest way is that you just replace this big sentence by 3 over d squared. That's what we prove.
Or just that constant?
Yes, just that number. Yeah, and actually yes, this would be expected values of the random initialization. So in some sense, if you initialize it in some way so that you get a little bit better than random initialization, then the rest of the job is
Maybe
done.
I ask a second question. You had two versions of Kac-Rice formula. What was the difference really?
Oh, the version that I didn't talk about is the version where you have a superlevel set. You want to count how many local maxima in a superlevel set. That's a straightforward extension of the usual formula. You actually, it doesn't have to be a superlevel set. Any pre-described set, you can count how many local minima or local maxima there.
So for your techniques, I think you need the functions to be differentiable, right?
Yes, yes.
So non-smooth function is out.
Yeah.
So one of the things you thought could happen for your tensor decomposition problem is that there are local optima that are not global optima,
Yep.
but from a random initialization, the path of the gradient descent algorithm avoids them.
Yeah.
Is there any problem where rigorously one can prove things like that?
No, not at all. So I don't know of any good techniques to really distinguish random initialization from arbitrary initialization. So, yeah, that's a fascinating question. I don't know how to. I don't have any idea for the moment. Any other questions?
The reception should be happening outside and trying to take